Welcome to the problem class, to the second problem class. We will do the exercise. Okay, the first exercise, basically what they say us is to do a retrosynthesis. We have these two pyridines, and basically if we think how we know to synthesize a pyridine, we have two options. One is the 1,5-dicarbonyl compound, the other is the Hansch ester synthesis. How we can differentiate a pyridine, how we can choose between one option or the other option, the 1,5-dicarbonyl compound or the Hansch ester synthesis. Basically, a good advice is to check the substitution in the pyridine. Okay? Here you can see that in the meta position what we have is two hydrogens, while in this pyridine what we have is two esters. When in the meta position we have an electron withdrawing group, that means that it's coming from a Hansch ester synthesis in 99% of the cases. While when we don't have electron withdrawing groups in the meta positions, probably will come from a 1,5-dicarbonyl compound. Of course, this is not perfect, there are other syntheses, but it's a very good approach. Okay? Will work in 99% of your cases. Then, first pyridine, we have two electron withdrawing groups in the meta position. That means that this could be a Hansch ester synthesis. The first step in all the synthesis of pyridines, what I recommend is that first try to do a dihydropyridine. The first retrosynthesis is convert this in a dihydropyridine. Because it's easy to do this disconnection, the next disconnection with a dihydropyridine, and moreover, when we do a dihydropyridine, what we know, that it's very easy to get the final pyridine. Basically, it's an oxidation, go from the dihydropyridine to the pyridine, and can be done with air, with DDQ, basically with any oxidant. Okay, then, next step, what we can do is to break one of the carbon-nitrogen bonds, which in this case is the same because it's symmetrical. In the other cases, could be more or less difficult, but both sides are okay normally. Okay, that means that we break this, and what we have is okay, and this can come from this, okay, from a ketone. If you take a look, this structure is not any more than an enamine, okay? Well, we have these two intermediates, and then if we take a look at this position is highly nucleophile, okay, and this position could be a Michael addition. That means if we break this bond, what we have is this, okay, plus and this is the same that okay, and how we can synthesize this? This is very easy. Basically, this is, we can break this. This is not any more than okay, another reaction between this ketoester and this formaldehyde to form this compound. And this compound will come from, basically, again, this is an enamine. That means that we can break this bond. We can form this from ketoester plus ammonium acetate. Okay? Right, this will be the retrosynthesis. If we want to do a forward synthesis, it's like we can start from here. We do an oven angle, like you did in the laboratory with Thomas. Okay, we form the alpha-beta unsaturated ester. On the other side, we take the other ketoester, that in this case is the same. We add ammonium acetate to form the enamine. Then this is a nucleophile. This will attack here to form this intermediate. Okay. One, we have this, we do the enamine. This is an imine. We do the enamine. We transform this in the enamine. And then this attacks here to form the other enamine. We form the dihydropyridine, and to get a final compound, basically DDQ or air. There are different options, but this is how it works. Okay? If you want to take a look this mechanism, I recommend that you do this mechanism step by step, not very fast as I did here. Okay? There are examples in the lecture notes, there are examples in the online video exercise and on the online video tutorial. Okay? Good. Then this is the High-Chester synthesis. This is how we do the retrosynthesis and how is the forward synthesis. And now we will focus in the second pyridine. Okay, the second pyridine we have in the meta positions two hydrogens. That means that probably this will come from 1,5-decarbonyls compound. Okay. First step, we will do the same than before. We will convert this in a dihydropyridine. Okay, this will simplify a lot the synthesis. When we have this, we can take a look that this is not anymore than an enamine. That means that this can be converted in with retrosynthesis. And then this is another enamine, and this can be converted. Whoops. In this 1,5-decarbonyl compound. Okay, remember how we can do a 1,5-decarbonyl compound? Basically, we can break this bond, and what we get is these two. This can come perfectly from a Michael acceptor, and this can come from this nucleophile, this ketoester. Okay, if we want to do a forward synthesis, we take the ketoester, we add a base, for example sodium hydride, okay, and we add the Michael acceptor. What we have is this compound, and then simply the carboxylation. We can add group CHO, okay, and we get the 1,5-decarbonyl compound. And then we add ammonia with a little bit of acid to catalyze the reaction, and we form the two imines and tautomerization to the N-amines, and we get the dihydropyridine, that to get the final product, basically DDQ or M. Okay? What is important of this exercise? The importance of this exercise basically is how we can differentiate the retrosynthesis between Hanchester and 1,5-decarbonyl compound. Okay? Remember, in the meta position, if there are 2 electron Lewis grabbing groups in each meta position, in the meta position, means that we will choose the Hanchester synthesis. If we don't have any electron Lewis grabbing group, we will choose probably a 1,5-decarbonyl compound. Okay, second part of the same exercise. Okay, this is how we can do the retrosynthesis of this compound. Okay. Well, this is a isoquinoline. Remember, first step always when we have a pyridine, a good step is that we'll simplify almost everything, is convert this in a dihydropyridine. In this case, the dihydropyridine that we can synthesize is this. Okay? Then, what we can do is break this carbon-carbon bond, okay? And this can be the addition of electron-rich benzene ring to a Bilsmeyer-Hack compound. And if you remember, this compound is a Bilsmeyer-Hack, that means that can be obtained from the amide that can be obtained from okay? If we want to do a forward synthesis, basically we start with the amine. We add acid chloride plus pyridine as a base. What we get is the amide, and then PCl3 to generate the Bilsmeyer-Hack and cyclization to get this dihydropyridine, to get the target molecule, basically DDQ, and we get the final compound. Okay? Okay, then the second compound is a quinoline in this case. If this is a quinoline, quinolines normally are synthesized by the addition of an aniline to an alpha-beta unsaturated ketone or aldehyde. Here you can see, we break this bond. This can be simply first, what we always need to do is basically to make, the first thing that we need to do is to transform this in a dihydropyridine. We will do it in a similar way than before. Okay. And then we can break this bond. This can come from the addition of electron-rich benzene ring to a ketone, a carbonyl group basically. With degradation, followed by degradation, and then this, we can break this nitrogen carbon bond. Sorry, it's missing a hydrogen here. And when we break this, this is basically a Michael addition. Between the aniline and this alpha-beta unsaturated ketone. Forward synthesis. Okay. First one for addition. To generate this compound, and then this ring, this benzene ring is electron rich, it means intramolecular attack to form in a first instant the alcohol that we can eliminate to form the dihydropyridine. Okay. And when we have this, to get the target molecule, basically again DDQ to oxidize, and we get the target molecule. Okay? Remember, for isoquinolines, we break this bond. For quinolines, what we do is this is coming from the addition of aniline to an alpha-beta unsaturated ketone. Second exercise means draw the mechanisms of the following reactions. They say that we can use NH3, this alpha-beta unsaturated ketone, this this one free ketoester, ethyl acetate, and benzaldehyde to generate this pyridine. Okay, again, it's a pyridine. We know several methods to synthesize pyridine, but if we take a look, we have two esters in the meta positions. That means that the most probably outcome is that we are doing this through a Hanchester synthesis. If we remember a little bit of the Hanchester synthesis, what we need is an alpha-beta unsaturated ketoester and a ketoester. Okay? That means we can synthesize first the alpha-beta unsaturated ketoester. That means if we react this compound, this ketoester, plus the aldehyde, plus piperidine in order to catalyze a reaction following the procedure that you did in the lab with Thomas, what we get is okay, and if you take a look, all this structure is very similar to all this part of the molecule. Okay? Then what we need? We need a ketoester. A ketoester that has to be with a metal here. That means we have this, the ethyl acetate, we do a Claisen condensation, we add etoxide, sodium etoxide for example, and what is happening basically is that we do the anion here, addition, elimination, and we get the ketoester that we want. When we have this, basically, we add ammonia. Normally ammonia we add in ammonium acetate. Okay, and we generate this enamine first. We do the imine and then tautomerization to the enamine. This is nucleophile, that means that this will attack the Michael. And what we will get this intermediate, again, tautomerization, imine, enamine, okay? And then the NH2, the resultant NH2 is attacking the carbonyl group to form an iminium first, and then tautomerization to enamine to generate okay, first step, tautomerization, imine, enamine. Second step, imine formation between this amine and this carbonyl group. Third step, tautomerization, imine, enamine to form the double bond here.